We have design op amps for different cases. I think now basically given any load, if it's possible in that technology, you should be able to design it. Okay. So sometime back we discussed limitations of the technology, right? Every transistor comes with its own parasitics. For instance, if you keep asking for more and more bandwidth, you will find that at some point the power dissipation starts growing sharply with bandwidth, much more than linearly. And then at some point it's not possible. But if you are well within that, now you should be able to design op amps for any specifications. Okay. So now we can look at some of the auxiliary circuits that are part of a chip. So we saw that every stage you have so many current mirrors, you will need bias currents for biasing various things. So that of course we can by using current mirrors. That is, if you have one current which is of a certain type, I'll explain what I mean by that. So then you can use either mirrors or cascode current mirrors if you want. Now, what is the type of current that I would need? Now, I can, instead of starting from scratch, I will use something that you have already solved, right? I think you've already solved these problems in the second assignment. So let's start from there. Was in one of the and I had one, right? And then this will be VB2 and so friends VD. Do you remember the question of VD as a current and what is the what was the current? Do you remember the answer? These two uh, plus okay. By the way, that I can change the. Give me a moment. Some. So VB1 and so I naught R is VB1 minus VB2. So the dimension of a bipolar transistor is the area. Increase the area. As usual, when I say n times the area, assuming n is an integer, I mean that you use n units of this and then connect them in parallel. this is upper, this is n unit. Okay. So then VB1 minus VB2 would be VT log. Basically, what happens with the area? The saturation current is proportional to the area, right? So exponential V, and this is proportional to the area. Okay. What IS is, it doesn't matter. VT log I naught by n times IS, which will be VT log n. Okay. So interestingly, IS goes away completely, right? So the current will be VT log n by R. Okay. Now, what is special about this? It was a big deal. So now, if I bias another transistor with the same P times, that is P times this area. What will be the current through this? What will be the current through the transistor? P times I naught. What will be the GM of this transistor? And it will be log n by R. Okay. So the thing is, the bipolar transistor's current is dependent on the bipolar transistor's GM is proportional to the current. It will change pressure proportional to absolute temperature. So in the 0 to 100-degree range, it at this circuit and gave this value of I naught, at which VD is 0. Then what happens is the GM is not dependent on temperature anymore, assuming R is temperature independent. Okay. So let's say you have R that is temperature, you can get it by using an external resistor, one external resistor or something like that. So then you will have basically a GM that is dependent on the resistor. Okay. And for instance, let's say this R is some polysilicon. The same type of resistor as a load. GM R prime would be P. Okay. So it has only a resistor ratio. So the gain will be precisely defined. Okay. So we went from constant voltage biasing for MOS transistors to constant current biasing because the GM would be less sensitive to transistor parameters and temperature, right? Now in bipolar transistors, constant voltage biasing is impossible anyway. You always use constant current biasing. There, but in both cases, there is still some dependence on temperature. Okay, it may be less than with voltage biasing. So in the case of bipolar transistor, the GM would have been inversely proportional to absolute temperature. But by now, what is the current here? This current itself is proportional to the absolute temperature. Okay. So by having such a current which increases with temperature, you reduce or you eliminate the variation of GM with temperature. Okay. Now this you do many times. In this case, it works out exactly. We know that GM is inversely proportional to absolute temperature. You have current directly proportional to absolute temperature, they cancel out and you get constant GM. In many cases, you will observe some variation with temperature, and maybe if it is also sensitive to bias, okay, bias current, you can have some other variation of the bias current with temperature and try to get the entire result to be more or less constant with temperature. Okay. So that is, you don't need to use constant current. Current need not be constant with temperature. It may be better to have it dependent on temperature, so that the overall parameter that you are looking for, that is constant with temperature. Okay. So in this case, it works out exactly. In some other case, it may not. Okay. So the first thing is to try and generate some current like this. Okay. So current that is proportional to absolute temperature, and it's called PTAT. It's abbreviated as PTAT. So it's called a PTAT current generator. So we'll see how to make that. So again, I won't start from scratch. We've already solved this problem. We'll try to use the results and hopefully the motivation is clear. By the way, the same assignment also had another problem, which of course looks very similar. In fact, it's the same circuit but with MOS transistors. Okay. If the MOS transistor is in weak inversion, it's the same as bipolar transistor, right? There is no difference. But here you are again asked to find the current when Vd equal to 0. What does that come out to be? When Vd equal to 0, it will be VGS1 minus VGS2 divided by R. And VGS1 itself is, what is it? Square root 2 I naught by mu Cox W by L. VGS2 is square root 2 I naught by mu Cox N times W by L times 1 by R. So if you solve this, what do you get? What will I naught be? So 2 by mu Cox W by L 1 minus 1 by R square. Okay. So you get some dependence like this. But the interesting thing is, again, what happens if I mirror this current and this is P times W by L? What will be the current in that MOS transistor, current through that MOS transistor? P times I naught. What will be the GM of that MOS transistor? So basically you can calculate, right? It is square root 2 times mu Cox W by L times, sorry, P times W by L times P times I naught. Okay. So now you can see I naught has one the mu Cox W by L in the denominator, so it cancels out completely. Okay. So this will turn out to be, basically we'll have 4 V square. Okay. So which is right, again all the temperature dependence has gone away except for R. So if you assume that you have a resistor with a which is constant with temperature, then GM also will be constant with temperature. Or even if R varies with temperature, if you make a common source amplifier with the same type of load resistor, the gain will become resistor ratio and that will be constant. So interestingly, exactly the same circuit works even when you have transistors in MOS transistors in strong inversion. Weak inversion, it is expected. It's the same as bipolar. So this type of circuit, in this case, it's not proportional to absolute temperature because we don't know what the, what is the temperature dependence of mu? It reduces, but how does it reduce? e to the power minus 3 by 2 or something, right? So this actually varies more than linearly, right? It's like 3/2 power of temperature, but whatever it is, the interesting thing is in this case also we have a constant GM. So these are also called constant GM bias generators or constant GM biasing circuits. Sometimes it is useful to use these. Okay. Yeah. Yeah, that's what we'll do. Okay. So now let me take bipolar transistors. So VD I have defined like this. Let me. So now, so what is it that I want to do? I want to get VD to be 0. That is, I want to vary I naught until VD becomes 0. So what should I do? How should I implement this in a circuit? Yeah, I mean, what's the general idea? I have to continuously vary I naught until VD becomes 0. Negative feedback. Okay. So first let's look at this in a little more detail. So let me call this, this is VB1, this is VB2, and this is I naught R. Okay. So let's say I put these voltages, all of these voltages versus the current on a logarithmic scale. Okay. VB1 versus current on a logarithmic scale. What will it look like? What is the expression for VB1? VT log I naught by IS. Okay. So versus I naught. I mean, that's what I meant here, right? So what is it? Straight line, obviously, because VB1 is VT log I naught by IS. So VB1 will be a straight line. What about VB2? So where will the straight line be in relation to this? What will its slope be? Where will that line be? VB2 line compared to VB1 line? Below this by VT log n. Okay, because it is the same thing. You have NIS in the denominator or minus VT log n. So VT log n. Okay. VB2 plus I naught R. What will that look like, you think? Or if I just I naught on a log scale, what will that look like? I naught R versus I naught, but I'm just using a log scale for I naught. What should that look like? Yeah, what is it? Just transform it, right? What will it be? What kind of curve will that be? Exponential. Okay. So basically it rises sharply. So what happens is when I naught is very small, okay, so the voltage drop across this will be negligible. And if I look at VB2 plus I naught R, it will be almost equal to VB2. Okay. And beyond some point, I mean, if I plot it like this, the voltage drop across R increases exponentially. Okay. So it will do that. And this is my magic point. So this is basically VB2 plus I naught R. Okay. So this point corresponds to what will be the current? What does this point correspond to? So basically where you have Vt log n by R. Okay. Now if I plot only Vd versus I naught, what does that look like? Vd versus I naught. What is it? Basically, it's like shifting the horizontal axis over there, right? So it is just that part of it. It will do something of that sort. Okay. So this is Vd versus I naught on a log scale. But basically, what I'm looking for is just just to see how it behaves. It is varying monotonically, right? So now, what is it that I should do? Basically, let's say now I have a variable current source for both these, right? And let's say that what is it that I should do? My negative feedback, you already said it should be implemented using negative feedback. What should happen? As Vd increases, I naught must go which way? It should decrease, right? Because Vd versus I naught is an increasing curve. So if you want to pull it towards 0, basically what should happen as when Vd is positive, I naught must go on decreasing. When Vd is negative, it must go on increasing. Okay. So when Vd is positive, I naught must decrease. So what should I do? I should just compare these two. Okay. And then integrate the and control, but there should be a negative sign because when Vd is positive, I want to reduce the current and so on. Is this okay? Any questions? So if I complete this negative feedback loop, it should settle to the point where will it settle to? When Vd equals 0, the integrator input is 0, which means you will have at that point the current sources will be providing Vt log n by R, and then you can take current mirrors and mirror them any which way you want. Okay. And assume that the two current sources are the same. So that means that, for instance, with the same gate voltage. Okay. There are many ways of I use PMOS transistor. So now Vd greater than 0, we said I naught must decrease. Okay. So now here I am controlling it with VGP. So if I naught must decrease, this is I naught and this is I naught. What must happen to VGP? VGP must go up. Okay. So I will control it. This let's say is a single op amp. Okay. What should be the that's what we want to have, op amp, upper one or lower one? So this is the signal. Okay. So this will be Vt. Of course, these are different sizes, 1 and n. Vt log n by r. Okay. Is this fine? This clear? Now you can do this. You can do exactly the same with the MOS transistor circuit also. If you choose MOS sizes when they are in weak inversion, you will again get to absolute temperature. If they are in strong inversion, then currents will go and settle to this. Okay. So here also you can. I didn't do it for the strong inversion case, but just like this, you can plot VGS1, VGS2, and this VD, and then see which way it varies. It will be in the same way. Same way in the sense the direction will be the same. The exact curve will be different. So the same circuit will work for the MOS transistors also, right? Huh. We'll now assume that it will be, see, we are mainly operating with CMOS process, so we'll assume that that's what we have. But if you have bipolar transistors, you can make the op amp using bipolar transistors also, or even this current source, you can make it with PNP bipolar transistor. Okay, that's not, I mean, it doesn't matter how you make them, right? Oh, what is that? Huh. Yeah, we'll see. First of all, I mean, that could be independently biased with something, but actually it will be biased from the same. I will show that. Okay. Is this fine? The idea behind this constant GM biasing. So you have some circuits which basically under some conditions, uh, their GM will be dependent on one particular resistor in the circuit. Okay. So that means the current will have some complicated temperature dependence. So now if you bias every other transistor using this, you will have constant GM property. Okay. And the same circuit works for bipolar and MOS. The bipolar stuff is very popular because of another reason. Like we'll get to one more circuit which is very, very important. Okay. But the MOS also is used sometimes. Okay. So this is called PTAT. PTAT means proportional to absolute temperature. PTAT current generator, and you can use it for many things. You could use it, for instance, to sense the temperature on the chip. Okay. So that is assuming that this circuit is very small. Okay. When you have a large, this is not the only way to do it. There are other ways, and some of the others are more compact. But when you have a large circuit like microprocessor, right, they have all kinds of complicated management. And one of them is also to change some parameters based on temperatures at different points, because you don't want it to burn out. Okay. Because you know that power of digital circuits is proportional to frequency. So if it is getting overheated, it is probably better to reduce the speed, okay, consequently reducing the power dissipation, than let something bad happen to it. Okay. So they will have all kinds of, I mean, many temperature sensors all over the chip, and you can see this could be one of them, right? So this will give you a current, and you can change that to a voltage that is related to the temperature. So this can also work like a absolute temperature sensor. So that's why this is very important. Okay. We'll see some more details of this, but I will keep showing the bipolar example, but the MOS works in the same way. Now, I said something about CMOS process, and I have used bipolar transistors here. This particular, by the way, both these, this will give you constant GM for MOS, this will give you constant GM for bipolar, but this is the one that gives you proportional to absolute temperature. The other one has some weird temperature dependence. It is, that temperature dependence is good enough to give you constant GM, but this is even more important than that, in that this gives you proportional to absolute temperature, okay, which is like a thermometer, right? So this is like an on-chip thermometer. So now, what do we do if we have only a CMOS process? To make PMOS transistors, we have an N well, and this is a P substrate, and this is our PMOS, right? That is the PMOS transistor. Now you can see, by the way, and then there will be an N well contact over there. But in this case, because you have all these junctions, you automatically have a PMOS transistor also. Okay, sorry, PNP transistor also, not a PMOS transistor. That is a PMOS transistor. You have P region here, N and P substrate. Okay, and also this is the most heavily doped. This is less heavily doped, and this is most lightly doped. And you know from your device physics that this is the emitter, that is the base, and that's the collector. Okay, so this parasitic transistor will be there even if the process is not intended to give you bipolar transistors. There are actually bi-CMOS processes in which you have proper bipolar transistors as well as CMOS. Those processes are more expensive, but this this particular thing you have this particular parasitic bipolar transistor is there even in CMOS processes. Okay. Now, of course, the problematic point here is that this collector is always connected to the substrate, right? So you have to, that restriction is always there. Also, what is a desirable feature of a bipolar transistor? I mean, what are some desirable features? You are familiar with bipolar transistors, right? You have done these in solid state devices. What's a desirable feature of bipolar transistor? Beta should be high. Okay, that is the main difference between bipolar and MOS, right? You have some base current, but the base current should be small, beta should be high. Now, what aspect of the bipolar transistor's physical structure makes beta high? What is it? I mean, the bipolar transistor has, in this case, P, N, and P regions, collector, emitter, and emitter, base, and collector regions. So, which aspect strongly influences beta? Base. What should the base be? It should be thin. Okay. If it is very thick, it's like having two separate diodes, right? What is the difference between a bipolar transistor? If you have P and P, this bipolar transistor and not two diodes. What is the difference between? Huh? Yeah, let it be. What is that? Huh? I don't think any of that matters. So basically, if you make the, if you had it like this, right, then this will be like that. Okay, it is this very thin base. What happens is basically all the carriers that are short from the emitter, most of it goes to the collector. The thinner it is, more of it that will happen. But the thicker it is, basically if it becomes very wide, then all of this current will go there. It's like having two separate diodes. So having thin base is an important thing, and that is not possible in this parasitic transistor, because this is not optimized to be a bipolar transistor. This base is whatever width you get over there, okay, and it will be wide, and the beta of this transistor is embarrassingly poor. It will be of the order of 1, okay, but it doesn't matter because we are not using it as a transistor to amplify. We will use it just as, we will connect it as a diode and use it as a diode, okay. So that way it is okay, but the beta of this transistor is very, very poor, and the collector is always tied to the substrate. So how will we deal with this now? Can we use this transistor? We can't use it everywhere, but at least for this PTAT generator, will we be able to use it? I mean, you have a transistor, but of course you can't touch one of its terminal. What good is this transistor? Is it useful? How will you use it? Fine, we somehow managed to get some crappy transistor in the CMOS process, but what will I do with it? Can we use it for any circuit? How will I use it in this circuit? Is it possible? So what I wanted was, sorry, the circuit I had was this one, right? Very obviously, and I'm only looking at this difference voltage. So very clearly, I can put the resistor on top of the transistor, and if I look at this VD, everything will be the same, right? This part is okay. And here I have used NPN. If I use PNP, what would it look like? PNP, diode connected PNP would be that way. Okay, I have VD. This is expected to behave in the same way. So what then? What next? What is the point of writing all this? What is the point of all this? What were we talking about actually? So basically, I said the issue here is the collector is connected to the substrate. At least in this particular circuit, collector is connected to the lowest potential or the ground. So we can use, at least for this circuit, those lateral bipolar transistors are useful. Okay. But of course, if you have proper bipolar transistors, use them by all means. But the point is, even in a purely CMOS process, you can still make this circuit. Okay. Now, let me elaborate the circuit by completing the showing the details of the single stage op amp. I'm showing PNPs now, but it doesn't matter. I mean, it's the same, right? We need to create this current source as he was asking. So, but let's say we do it by biasing it with some current mirror. Okay. And this is where we complete the feedback loop. Okay. the PTAT cell, and that's the single stage op amp. Okay. So now is the circuit complete? Is there something else that may be required? I mean, given that it's a negative feedback loop. Capacitor, where? So basically, it does have, it does have one gain stage, and the other one, it will not have a lot of gain. Okay, so you may or may not need a stabilizing capacitor, but if you do need one, you can, for instance, connect a large capacitor there. Okay, and then make that the dominant pole, and the circuit will be well behaved. Okay. Is it okay? Now, how do you use this? You can take this current, mirror it as many times as you want. Okay, and use it wherever. And if you want, this is a current source, that is, it pushes current out, and then you can use NMOS mirrors to pull current if you want to. Okay. So this is these are current mirrors to provide this bias current to other circuits. Okay. And of course, you can use W by L ratios as required to scale the current. You don't need to, I mean, if this is operating with 1 microamp, you don't need to use 1 microamp everywhere. Just multiply it up and use it. Okay. Now, one of the things that is commonly done is also you can bias the op amp from here. Okay. So that is assuming the circuit is operating properly. This is giving some PTAT current, right? Otherwise, what would you have to do? So this you can, one possibility is you take this and use some other current mirror to provide the current, and then you use some resistor there, because you can't use some current source, because the next question will be where did that current source come from, right? So you can either use independent biasing, or I will show it in the same circuit. You can use self biasing. It's one of these two, right? I mean, I didn't want to draw it again, so I showed this. So instead of using this, anyway, I know that the whole purpose of this is to generate bias currents, and I use one of those bias currents over there. Okay, so that will also work, right? Now the self-biasing circuits, and in this PTAT cell, all this type of circuits have one particular problem, that is startup. Because if it doesn't start, then the bias currents will be 0, and if the bias currents are 0, the op amp is not working, and there is no negative feedback to start it. Okay, so that is a problem we have to solve. There are circuits known as startup circuits which will do that. We'll discuss that briefly. But basically, that is something that has to be there for any self-bias circuit. Okay, because one possible operating point for the circuit is all branch currents are 0. Okay, and then it will never get out of that, right? So basically, the self-biasing is what is used typically. But it needs a startup circuit. Okay, and that part is true whether you do this for MOS or bipolar or any variant of this. Okay, any questions? Right, so you will still need a I mean, you can find ways of starting it, but yeah, you will need to make some arrangement to start, because as I clearly pointed out, if these two voltages are zero, right? Even if you have bias current here, not bias current, let's say you have a gate bias here, so that it behaves like a current source, but if its VDS is non-zero, if the input voltages of the op amp are zero, what happens is that this will be in deep triode region, it will be in zero, and the op amp itself will be off. Okay, if the input, you know that this op amp works only for common mode voltages which are above a certain value. So either you have to make some arrangement to use PMOS and have some startup, or have some other startup condition. Okay, so these circuits definitely have that problem, even without self biasing. Okay, or even here, I didn't show it because I showed it on a log scale. So you can see VD equal to 0 not only at this point, at I naught equal to 0 also VD is 0, right? This difference voltage is 0 at one particular, I mean at this operating point, but also at I naught equal to 0. So that's a valid solution as well to the circuit. Okay. So now we have some way of getting a current that is proportional to absolute temperature. We may want to get a current that is constant, or a voltage that is constant. How would we do that? A constant voltage, everywhere we have references, right? We kept writing VCM ref and so on everywhere. So if you have one constant voltage reference, then you can scale it to get anything else. But how would I get a constant voltage or almost constant voltage? What should I do? I mean, during analysis of circuits, you have been told to take some voltage as constant. What is that? Could you use that? What is that? Many times you, at least for the sake of analysis, you are given some number. Use this for this voltage. What is it? Huh? VD-SAT. Why is that? That's not a voltage, right? I mean, that's not a voltage that comes out. Huh? Which is the one? I mean, that very commonly you use something as a constant in all this circuit analysis, right? Which one? What is it? VDD. No, how do you get VDD? What is the first assignment in analog circuits? What type of circuits did it have? What type of elements did it have? Huh? Voltage? How do you make a voltage regulator? What is it? Yeah, diode. What, I mean, how do you analyze circuits with diodes? When you assume that when it's on, the voltage is a constant. Okay, so that is because, of course, it is not constant. The IV curve is an exponential, and because it's an exponential, you assume that in some reasonable range of currents, the voltage varies over a very narrow range. Okay, so now you can use that as a feature also, right? So what it says is that if I have a resistor and a diode means diode connected bipolar transistor, what should this voltage be? For analysis, you will just say 0.7. Okay, so potentially we can say that, hey, look, I have a constant 0.7 volts here. Okay, but the question is, how constant is it? Because the resistance can vary, the transistor characteristics variation. Current. Okay, I get some VB. The current is constant. Now, if I plot VB versus T, what will that look like? VB is VT log yes. Okay. So what will VV look like? Decreasing. How is it clear from this? Anyway, please recall all the relevant stuff and we'll continue the discussion. Okay. How much does it decrease? It is correct. For a constant current, it decreases with temperature. But how much does it decrease for every degree? How much? Do you remember the value? I think this is commonly discussed when you discuss diodes and bipolars. Minus 1.5 to minus 2 millivolts, minus 1.8 millivolts or so per degree Celsius. Okay. So it's actually not all that constant. How much does it vary over 100 degrees? If you assume that slope is constant. 180 millivolts. The voltage itself is 700 millivolts. So it's a very substantial fraction of that. So it's actually not a great regulator. Okay. That is with temperature. With other things, it may be okay, but its temperature variation is too much and we have to do something about it.